Last week we discussed the circuit model, the quantum circuit model for quantum computation, and we discussed the fact that arbitrary quantum circuits, that is, quantum circuits that involve arbitrary unitary transformations on your input qubits, can build from a very small number of different building blocks. In particular, single qubit operations, and this can be further limited to just two types of gates, namely the Hadamard gate and the T gate, and just a single type of two-qubit gate, namely the C0 gate. You don't need any gates involving more than two qubits, and you don't need any other type of two-qubit gate. So in principle, you can always reduce it to just this very small set of elementary gates, to this universal set. And then at the end of your calculation, when you want to extract a classical result, then you have to perform measurements on the output qubits. What I would like to show you today is that, at least in principle, you can even do without the unitary operations and perform a computation with measurements only. And as I said, this is something completely unheard of in the classical world. We will not discuss sort of practical applications or whether this can be built in the lab. It's going to be a proof of principle. Just I want to give you an argument why in principle this can happen. And it just serves to illustrate it illustrates the big difference between the quantum domain and the classical domain, which manifests itself also in the way of doing computation. I show you a very, very simple circuit which illustrates the basic idea. Imagine you have just a single qubit in an arbitrary state psi. This is the lower state that I noted here on this page. The circuit will involve a second qubit, an auxiliary or so-called ancilla qubit, which starts in the basis state 0. So that is fixed. The qubit of interest is the one which can be in an arbitrary state psi. What we would like to achieve is a unitary transformation of that state psi with an arbitrary unitary transformation. So it's not limited in any way. So it can be any unitary transformation. And we want to achieve that unitary transformation using measurements only. Now, in fact, this little circuit will involve two measurements in a row, in sequence. The first measurement is a measurement, so it's not a single qubit measurement in the standard basis. So it's not the standard measurement that we have encountered previously. All this only works if you allow more complex measurements, but still they are just measurements. So here we have a measurement on both qubits. So it's a measurement of a 2-qubit observable, which I call B. And specifically, this 2-qubit observable that we measure has this particular form. It's the sum of two terms. Both terms are tensor products of operators. And the first term is with a 1/2, it's Pauli x minus I Pauli y operator. This is the operator acting on the first qubit. Tensor, a unitary operator, and that's precisely the unitary operator that we would like to emulate with our measurement. Plus a second term which looks very similar, only you have change of sign in front of the imaginary unit, and you have the U dagger instead of the U. First of all, we have to convince ourselves that this is really unobservable. And so we have to check that this operator is Hermitian. Now that's pretty straightforward to see if you take the first term in the sum and then take its Hermitian conjugate. Now the Pauli operators, they are Hermitian. So when you take the Hermitian conjugate of the first factor of the tensor product, then all that changes is the sign in front of the imaginary unit. And that's precisely the first factor that you have in the second summand. Yeah, so the second term in the sum, and the first factor in the second term of the sum is the Hermitian conjugate of the first factor in the first term. And likewise, when we look at the second factor in the tensor product, then in the second term in the sum you have the U dagger, which is the Hermitian conjugate of the U, which you have in the first term. So you see that in the sum, the second term is the Hermitian conjugate of the first term, and hence the sum of the two is Hermitian. So it is indeed an observable that we can measure. We don't worry about how we can do that in the lab, how we construct the measurement device for that. But it's conceptually an observable that we can measure. Now this particular observable has two further properties that will be useful for the analysis of our circuit. The second property is the square of this observable B equals the unit operator. Now, in order to see that, we can write the observable in a slightly different fashion, and then it's easier to see. Now, remember the properties of the Pauli operators. One of the properties was that Pauli x times Pauli y is I Pauli z, for example. Or y Pauli z is I Pauli x. Or Pauli z Pauli x is I Pauli y. And the last one we shall use. We shall replace the Iy by z Pauli x. This means we can rewrite the observable B as 1/2, and then we have x minus zx. We can factor out the Pauli x. So then we have unit operator minus Pauli z Pauli x tensor U, and for the second term in the sum we have just the other sign, so we have I plus Pauli z x tensor U dagger. Now, if you remember the form of the Pauli z matrix in the standard basis, that's a diagonal, within the diagonal plus 1 and minus 1. Now, if you take the unit matrix and subtract from that the Pauli Z matrix, then in the upper left, you'll have a 0. In the lower right, you will have 2. And then you multiply this by 1/2, and then this gives you a matrix with just one non-zero entry in the lower right, and that's the 1. And that's the projector onto the basis state 1. In a similar fashion, you can argue here in the second term, in the sum with the plus sign, that this is the projector onto the basis state 0. Then in both cases you apply the Pauli X from the right. Now the Pauli X flips the basis state. So actually we can write the first term as the dyad 1, 0 tensor U, and the second term we can write as the dyad 0, 1 tensor U dagger. Now this is a more compact way of writing the observable B. And now let's see what happens when we take the square, B square. Then we have the first term squared, but this gives 0 because we will have the product 1, 0, 1, 0. Yeah, so in the middle there will be a scalar product between basis state 0 and basis state 1, but they are orthogonal and this vanishes. Likewise, the square of this term vanishes because here for the first factor we will have the dyad 0, 1 times the dyad 0, 1, and in between there will be a scalar product 1 and 0. They are orthogonal and this vanishes. So we are only left with the mixed terms, and there we have well, two possible orderings. We have either 1, 0 tensor U multiplied by 0, 1 tensor U dagger, or we will have the other ordering, that is 0, 1 tensor U dagger multiplied with 1, 0 tensor U. So here we have to do it factor by factor. So here we have the dyad 1, 0 multiplied with the dyad 0, 1. In between we have a scalar product of the basis state 0 with itself. It's normalized, so this is 1. And we are left with 1, 1. And U times U dagger gives the unit operator in the Hilbert space of the second qubit. So this is tensor unit. And for the second term in the sum, it's the same logic, only that we have here, when we multiply the two dyads, we get 0, 0 and tensor unit. Yeah. So this is then, this we can take together. We can factor out the unit operator for the second qubit in the second qubit Hilbert space, and in the first qubit Hilbert space we have 1, 1 plus 0, 0, but the sum of the two is again the unit operator now in the Hilbert space of the first qubit. So we have unit operator for the first qubit, tensor unit operator for the second qubit, and this is of course nothing but the unit operator in the 2-qubit Hilbert space. So let me perhaps write it like this. So indeed, the square of this 2-qubit observable gives the unit operator in the 2-qubit Hilbert space. This immediately tells you something about the possible eigenvalues of that observable, because also the eigenvalues then must satisfy the condition that their square is equal to 1. And this is only possible for two eigenvalues, namely +1 and -1. So you already know that the spectrum of this observable can only contain the values +1 and -1. And now the third property that I would like to show you is that when you apply the observable B, the operator B, to the tensor product of basis state 0 for the first qubit and this arbitrary state psi for the second qubit, then the result is basis state 1 for the first qubit, tensor the unitarily transformed state for the second qubit. And let me briefly show you why that is. Again, we will start from this representation of the 2-qubit observable B, because here you see it immediately. When you apply this operator to the tensor product of 0 times psi, then this second term here will not contribute, because when you apply this dyad 0, 1 to the basis state 0 of the first qubit, you get a scalar product of the basis state 1 with the basis state 0, and that vanishes. So this second term here will not contribute when applied to the tensor product 0 times psi. Only the first term will contribute. And here, when you apply the first factor here to the basis state 0 of the first qubit, you get the scalar product of basis state 0 with itself. This is 1, and you are left with basis state 1. And the unitary operator U is applied to the state psi of the second qubit, and you get the transformed state U psi. So this is precisely what I wrote on that slide. This result has another interesting implication. The tensor product state 0 with psi, that's precisely the state, the initial state on which we perform the measurement. And we may wonder, what is the expectation value of B in that state? And that is the observable B sandwiched between the state in which we perform the measurement and the state in which we perform the measurement. That's the tensor product of basis state 0 tensor psi. What we just discussed was that when the operator B is applied to this tensor product, the result is basis state 1 tensor U psi. And now you can immediately see when you calculate the scalar product of these two tensor product states. so 0 tensor psi, scalar product with 1 tensor u psi, then you do that factor by factor. So you have the scalar product of 0 with 1 times the scalar product of psi with u psi. 0 and 1 are orthogonal basis states. So their scalar product vanishes. And this means that the expectation value of B is 0. This in turn implies that the two possible measurement values, we discussed the fact that the spectrum of B contains only +1 and -1. So these are the two possible measurement values. The expectation value of B is the weighted average of these possible measurement values, weighted with the respective probability. This implies that the probability of measuring +1 in the state, in our initial state, and the probability of measuring -1, they must be equal. They must both be equal to 1/2. Okay, so we've learned quite a bit about this peculiar observable B. We know it has measurement values +1 or -1, and they occur in this state, 0 tensor psi, with equal probability 1/2. After the measurement, the state changes, depending on which of the two values we measured. The rule is that after measurement, the state is projected orthogonally onto the eigenspace that corresponds to the value that was measured. So if +1 was measured, then the initial state is projected onto the eigenspace corresponding to the eigenvalue +1. So we have to apply to the state 0 tensor psi the projection operator that does this projection. Now, since the observable B has only eigenvalues +1 and -1, this projector is easily written. It is the sum of unit operator plus B times 1/2. This does the projection. Think of B in its eigenbasis, so diagonalized. On the diagonal, you have only the eigenvalues +1 and -1. You add to that the unit matrix, then all the ones of the unit matrix cancel with the -1s in the B, and with the +1s in the B, they add up to 2, then you divide by 2. So you have then ones where you had the eigenvalues +1, and you have zeros where you had the eigenvalues -1. And the result is that it's a projector, and it projects precisely onto the eigenspace associated with the eigenvalue +1. Likewise, for measurement result -1, then the projector is given by 1/2 unit operator minus B, and this is applied to 0 tensor psi. And after the projection, the result is in general no longer a unit vector. So we have to renormalize then that projected vector, but we don't care about this normalization factor. Imagine this is just a proportionality, and here I write up to normalization factor. Let me summarize this in a slightly more compact form. So the tensor product is mapped to up to normalization factor, so I write a proportionality sign. I plus or minus b applied to 0 tensor psi. We can multiply out this bracket, so the unit operator obviously does nothing, so this gives us 0 tensor psi. And then we have plus or minus the operator b applied to 0 tensor psi. And here we use, once again, our earlier result. The effect of the operator b on this tensor product is basis state 1 tensor u psi. So here we have 1 tensor u psi. So let's at this point go back to the circuit. And we know after measurement of b, so that the two possible results occurred with equal probability, one of the two. And after this measurement, the two qubits are either in the state 0 tensor psi plus 1 tensor u psi or minus 1 tensor u psi. Now comes the second measurement, and the second measurement is performed on the first qubit, on this ancilla qubit only. And it determines in which of the two basis states the first qubit is. For this measurement, for this second measurement, there are two possible outcomes. Either +1 or -1 for Pauli Z. So measurement of Pauli Z is precisely a measurement in the standard basis because Pauli Z is diagonal in the standard basis. And since the state just prior to this second measurement was this one here in the last row. You see, regardless of the outcome of the first measurement, the two differ only by the sign here, plus or minus. Regardless of the outcome, the state after the first measurement is a superposition with equal amplitudes or equal absolute value of the amplitudes of these two states, tensor product states. In particular, when you now perform in the next step, you perform a measurement only on the first qubit in the standard basis. Then you will find 0 with probability 1/2, or you will find 1 with probability 1/2. And after that measurement, that second measurement, you will have to do yet another projection onto the eigenspace associated with the result of your second measurement. If the result of the second measurement yielded +1 for Pauli Z, then the associated eigenstate is the basis state 0. So then you project onto this state. So then after the second measurement, the two qubits are in this first tensor product state. If, on the other hand, in the second measurement, you measured -1 for Pauli Z, the associated eigenstate is the basis state 1. And then you have to, afterwards, you have to project onto that eigenstate. And then your state after the measurement is this tensor product. Let's now consider these two cases. When your outcome was +1, you project onto basis state 0 for the first qubit. Then the composite state of the two qubits is again the tensor product 0 tensor psi. In other words, it's precisely the state that you started with. If this happens, you go back and you repeat the circuit. Yeah? So you go through this circuit as often as necessary until, for the first time, you measure in your second measurement the outcome -1. And when the outcome is -1, you have to project onto the basis state 1 for the first qubit. And then the state after measurement for the two qubits is the tensor product state 1 with the transformed psi, with u psi. And then you stop, because then you have the second qubit in the transformed state that you wanted to have. Yeah. Then you've achieved the unitary transformation of the second qubit, and then you stop. You see that this algorithm is probabilistic. Yeah, it's not guaranteed that in the first run or after a definite number of runs, you have the second qubit in the desired state u psi. But you just have to run it as often as necessary until eventually the second measurement gives you the outcome -1 for Pauli Z. And then you stop, and then you have the qubit in the desired state. The expected number of runs is the sum. You need at least one, of course, and in principle can go up to infinity. And then you need n runs with a certain probability prob of n. So you take, and then you take the weighted average, and this gives you the expected number of iterations. What is the probability that you need exactly n iterations? Exactly n iterations means that in the first run, you get the outcome for Pauli Z, you get the outcome +1. And that occurs with probability 1/2. In the second iteration, you must have again the outcome +1, which again happens with probability 1/2. And so on, until the nth iteration, where you need the outcome -1, because after the nth iteration you stop. And that again happens with probability 1/2, because all the runs are independent of the previous one. So this probability is 1/2 to the power n. So you have here the formula, it's n divided by 2 to the power n, sum over all n. And you can convince yourself, it's just a little exercise, mathematical exercise, that this sum is equal to 2. So the expected number of iterations is 2. This concludes the discussion of the measurement-based computation. So this is really a little Mickey Mouse example, but it shows you the basic idea, that you succeed in transforming a qubit from an initial state psi to an arbitrary transformed state u psi using just measurements. Now this can be extended to transformations of more than just one qubit, to multiple qubits. So you can implement by way of measurements not just single qubit transformations, but also multiple qubit transformations. And this then means that measurement-based computation is just as universal as the gate-based computation. It's enough to show that with measurements you can emulate arbitrary single qubit transformations and the C0. And since single qubit transformations and the C0 form a universal set, and if both can be implemented with measurements, then automatically measurement-based computation also is universal.